Well, today we'll see the second module of the course. In this module, we are going to come across the concept of relations. In this, we are going to see the topics such as domain and range, inverse of relation, composition of relations, different types of relations, and partial order relations. In this week, we are going to see up to the partial order relations. In the next week lectures, we'll see remaining parts. In this lecture, we'll mainly focus on the domain and range, inverse of relations. Well, what is meant by a relation? Relation means there should be some associativity between two entities. Then it is said to be a relation. Okay. Ramu drives car. So here is an association is there, drives. Okay. Like that, some association must be there between two entities. Then we can say it is a relation. In case of set theory, how we can represent the relations? That is what the main agenda of this particular topic to discuss. If you look at the general definition of relations, a relationship between elements of two sets, A and B, is the set of ordered pairs with the first element taken from A. Set of ordered pairs, okay, in which first element taken from A and their second element taken from B. Since this is a relation between two sets, it is called as binary relation. If it is between three sets, then it is ternary relation. Okay. For example, in general statements, binary relation is Ramu drives a car. This is a binary relation. Two entities are there, Ramu and car. And we are going to make an association between these two entities. While coming to the ternary association, there will be a relation between three entities. For example, Ramu is a programmer, knows C language and working on compiler project. Here, three entities are there, project, programming language, and the programmer. So the programmer who knows C programming language is working on the compiler project. So here three relations are there. So which is called ternary relation. Like that, as the number of sets involves, that is the relation, it increases, and the complexity of the relation also increases. So here, definition, let A and B be sets. A binary relation from A to B is a subset of A cross B. A binary relation R is a subset of A cross B. That means whatever the resultant subsets that we will find in the relation R is a subset of A cross B. That is, cross means here Cartesian product that we have seen in the last lectures. Whatever the Cartesian product of A cross B that you get, from that some of the pairs will belong to the relation R. Okay, in such a cases, we'll call it as the R is the subset of A cross B. This relation, how we can mention that A is related to B? That means we are going to mention it as a capital R. Okay, we are going to represent with a capital R as the symbol. The notation A capital R. This is the symbol. Here we are going to represent A capital R. B denotes that A comma B is belong to capital R. When can you say that it is not belong to the relation R? So you are supposed to place an underline between, that is A, R. If whenever you mention underline, that means that A comma B is not belong to R. This is the way you are supposed to represent a relation between two elements in two different sets. We'll see some more examples here. A relation R for a set A to set B is a subset of A cross B. Just now we discussed it. Now, the representations will be done like this. If A comma B belongs to capital R, which is the relation R, we say that A is related to B, and we'll write as A capital R B. If it is not belongs to R, then belongs to symbol and a cross mark over that. We say that A is not related to B and write A cross, that is AR underscore. You can make it, you can write it as A capital R with an underline below the capital R B. R, you can strike off R there itself, so it will also mention it as A is not related to B. And when can you say that A is equal to B? If A is equal to B, we often say that capital R is the relation which belongs to A cross A, is a relation on capital A. That means the elements, the pair of elements in the set A and set B are same. Okay. Now let us look at the example. A is equal to 1, 2, 3 and B is equal to X, Y, Z. Let A is equal to, let our capital R relation R is equal to 1 comma Y, 1 comma Z and 3 comma Y. Then R is a relation from A to B. Is it or not? So obviously it is yes, since R is a subset of A cross B. Whenever you go for the A cross B, then you will get 1x, 1y, 1z, 2x, 2y, 2z, 3x, 3y, 3z. That is the whole set that you will get after the Cartesian product of A and B. Now, the given relation R is having the 1 comma Y, 1 comma Z and 3 comma Y. So these three pairs are the subset of the Cartesian product A cross B. So hence we can say R is a subset of A cross B, and this particular relation R is a relation between the A to B. And this can also be represented with the elements in the set can be represented like this. With respect to this relation, the representation of the relation between the elements in the sets will be represented like this: 1 capital R Y, 1 capital R Z, 3 capital R Y. So this is also one way of representing the relation between the elements in two different sets. At the same time, you can also mention one, there is no relation, that is R cross, that is just strike off the R and X. Like that, there is no relation between 2 and X and 2Y, 2Z, 3X, 3 and 3Z. Here is an example why this particular, in general, in computer science and in computer science courses, where this relation will be used exactly. These relations will be used in, especially in the database analysis and social network analysis and this kind of things, in which you will find, in especially in social network analysis, who is the common friend of these two elements, or these two entities, or these two persons, we can say. You pick up two persons and you are supposed to find out the common friend of these two persons. Okay, so then obviously there should be a relation between, okay, the person 1 and his friend, okay, and that friend and the person 2, or maybe person 1 to the person 2. These are the relations you are supposed to check out. And also you have to identify the relation between the students and courses. So let S be the set of students and C be the set of courses. Let R is equal to S comma C. Student S is taking the course C. Many students may take the same course, which is called many to one relation. A single student may take many courses, which is also a relation type, one to many relation. Okay. So these are the different ways of relations that we'll represent using this mathematical representation of relations. Here is another example. When A comma B belongs to R, A is said to be related to B by R. Let P be the set of people, C be the set of cars, and D be the relation describing the person who drives which car. So P is equal to Sumit, Akash, Peter, Johnny. So these are the people which are there in the set P, and the companies, the car companies were represented in the set C, and D is the set between the persons and the car, who is driving which car. Okay, so this means that Sumit drives Mercedes, Johnny drives the a Mercedes and a BMW, and Peter drives a tricycle, and here there is no relation of the Akash and any other car, so that is the reason we are going to mention it as Akash does not drive any of these vehicles. Here is another example, again the same course example, students taking the courses. You can go through this, it's not a complex example. Let A be the set of students in your school, let B be the set of courses, let R be the relation that consists of those pairs A comma B, where A is a student enrolled in course B. So here some the set of students were given, set of courses were given, and the relation between the students and the courses have been taken. So whenever you are going for at the beginning of the semester, whenever you go for the registration, so obviously at the time you will mention what are the courses you are going to opt in this particular semester, and that particular opting courses, the related credits, some of the credits should not cross so and so limit. So by taking that into consideration, you will opt the courses. So in the same way here also, a pair was given, and for instance, an example was given. You can go through it. Now, on a set or on a two or more sets, you cannot say only one relation exists. They may exist multiple relation. So here is this particular slide will give you an example that consider these relations on set of integers. Now, here around 6 relations were defined. According to these 6 relations, the given set of pairs in both the sets A and B will be related. How? R1 is equal to A comma B. Okay, this is a relation defined. So when you can form the relation of A comma B with respect to R1, when A is less than or equal to B. That means the element in the first set is less than the element in the second set. Then you can make a pair. So this is what the relation that you are going to mention here. While coming to the relation 2, R2 is equal to A comma B if A is greater than B. R3 is equal to A comma B whether A is equal to B or A is equal to minus B. R4 is equal to A comma B only if A is equal to B. Here 2 cases are there here. In the R3, A is equal to B, or here R option is there. Okay, that means if A is equal to minus B, in such a cases also this R3 will hold. Okay, but if A is equal to B, then you can opt for the R3 and also for the R4, because R4 is giving you A comma B if A is equal to B. While coming to R5, A is equal to B if A is equal to B plus 1. That means 1 greater than the A. Next is R6. A is equal to A comma B is the pair you can form if the sum of A and B is less than or equal to 3. In these cases, these are the different rules were framed. Which of these relations contain each of these pairs? So here 1 comma 1, A is equal to B, R3 holds. Okay, R4 will also hold. And 1 plus 1 is equal to 2. This is A plus B is less than 3. Okay, this will also hold. And A less than or equal to B, this will also hold because less than R. Okay, in any of the cases, this will also hold. So like that, each pair will fall under which particular relation that can be categorized based upon the condition that was mentioned in the relation. So that means with this you can come to know that in any pair of sets, or in any pair of elements, okay, there will not be only one relation holds, but depending upon the condition that you mention, the relations hold. So here 6 relations was mentioned with each relation consisting of its own condition. And if you look at the solution, note that these relations are on a infinite set, and each of these relations is an infinite set. Checking the conditions that define each relation, we see that 1 comma 1 is in, just now as I told you, R1, R3, R4 and R6, because A is equal to B, A less than or equal to B, and in the R6, A plus B is less than or equal to 3. So these 3 relations conditions were satisfied. That is the reason 1 comma 1 is a pair which falls under the R1, R3, R4 and R6. In the same way, 1 comma 2 is in R1 and R6. 2 comma 1 is in R2, R5 and R6. 1 comma minus 1. So obviously you can easily identify it, because in R2 it was mentioned the condition as A greater than B, 1 is greater than minus 1. So hence R2, and R3 is A is equal to minus B. A is equal to minus B. That means 1 is equal to minus 1 here. So hence it is holded. While coming to the, and also R6, that is A plus B is less than or equal to 3. While coming to the 2 comma 2, it is in R1 comma R3 and R4. The same analysis you are supposed to make for placing the this particular pair 2 comma 2 with respect to the given relations. How many different relations can be defined on a set A with elements, with n elements? So if a set A is consisting of n elements, how many relations that you can make? A relation on the set A is a subset of A cross A. So whenever you make the subset of A cross A, how many elements you will get? Automatically you will get a, we have seen in the last lecture, A cross A is equal to, you can make A square, that means n square elements that you will get. Okay, A cross A means A cube, like that you can form. So like that, how many Cartesian products you make on the same set, that is the power that you can make use of. So here, how many elements are there in A cross A? There are n square elements in A cross A. So how many subsets you will get? Does it have? So whenever you have n elements in A, how many subsets you will get? How many subsets you will get? 2 power n, right? So the number of subsets that we can form out of a set with the m elements is 2 power m. This is a generalized explanation, or this generalized formula we have seen in the last lecture. So since there are n square elements in n cross A, so you will get the 2 power n square, okay, subsets can be formed out of A cross A. So final answer is, we can define 2 power n square different relations on A. So whenever I'm going for the explanation, so whenever this kind of things are there, you don't need to write everything on the register, in the register. However, you can make note of how many different relations can be defined on a set A with n elements, just to make a note of the direct answer, that is 2 power n square, for easy remembrance. Okay. Now we are going to define 2 new terms in this particular relations. That is, one is domain and range. Okay. The domain of a relation R is a set of all first elements. Please remember, all first elements of the ordered pairs which belongs to R, which is denoted by dom of R, which is the domain of R. And range means, the range is a set of second elements. Okay, here is the first element. Domain means first elements. While coming to the range, it is second elements of the ordered pairs which belong to R, and also denoted by the range, RAN, of capital R. For example, A is equal to 1, 2, 3, and B is equal to X, Y, Z. And here is a relation formed 1, Y, 1, Z, and 3, Y. Now, what is the domain of this particular given relation R. The domain of the given relation R is the first elements of the ordered pairs. What are the first elements? 1, 1, 1, 3. In this 1 is repeated. So take only once. So the domain of the R is domain of R is equal to 1, 3. Then range means the second elements of the ordered pairs Y, Z and Y. So Y was repeated for 2 times. So you have to take only unique element. So you take only once Y. So the range of R is range of RAN of R is equal to Y comma Z. So this is the way domain and range of a relation has to be defined. So domain is the first elements of the ordered pair, okay, and range is the second elements of the ordered pair, and no duplicacy must be considered, okay. So this is the way you are supposed to use the domain and range of a relation. We'll have some examples. A is equal to 1, 2, 9. B is equal to 1, 3, 7. If the relation R is equal to, that means we have seen the relation A comma B is the relation if A is equal to B. Okay. Then R is equal to 1, 1 and 3, 3. Then the domain will become 1, 3 and range will become 1, 3. If the relation is less than, we have seen the first relation, which is second relation, where we can form the relation A comma B if A is less than B. In such a cases, we can make the relations like 1, 3, 1, 7, 2, 3 and 2, 7, and here domain will become the first elements in the ordered pair 1, 1, 2, 2. Here 1 is repeated and 2 is repeated. We have to take only once. So domain is equal to 1, 2. And range will become 3, 7, 3, 7. So we are supposed to take only 3, 7, which is range. In the same way, if a relation R is greater than, then A is, that is, the relation R is equal to A comma B pair if A is greater than B. In such a cases, R is equal to 2, 1, 9, 1, 9, 3 and 9, 7. So the domain will become 2, 9 and the range will become the second elements of the ordered pair 1, 3, 7. So this is the way we'll define the domain and range of a relation. Now, so far we have seen the relation and finding the domain and range. Now this is the inverse relation. Okay, inverse relation means just flip the pairs. Okay, inverse relation means just flip the pairs, and a relation R is mentioned as capital R, then inverse will be mentioned as R power -1, like that. So that is what the inverse relation is. So two sets are inverse of each other if the domain and range of each set is flipped. Write the inverse of 2, 3, 4, -7 and -5, 0. These are the pairs which are available in the relation, say for example R. Then its reverse will be just flip the pairs 3, 2, -7, 4 and 0, -5. I think you don't have any difficulty in this. Just inverse means just to flip the pairs. So find the inverse of the relation X is equal to X, that is the X ordered pairs, X, Y pairs, -1, -2, 0, -1, 1, -1 and 2, -2. The domain and range of the relations and its inverse. Say for example, the function, we'll consider this function f of x as the relation, then inverse will become the f inverse of x. So in this, x is equal to -2, -1, -1, -2, because just to flip from y is equal to y as x and x as y, then you will get these particular values. And if it is the relation, if the domain is like, the domain will become like this, -1, 0, 1, 2 is the domain of the function x, and range will become -2 and -1, because -2 repeated twice here, and minus 1 also repeated twice. So minus 2, minus 1 was considered. Now if you make the inverse, the domain will become the range of the function f of x, and range will become the domain of the function f of x. So just you interchange this. So which will become the domain and range with respect to the inverse and normal function. So far we have seen the how you will represent the relations, and how the what we call combination of the relations will be considered, and what is the domain and range of the relations, and what is the inverse relations. Now we'll see the relations, combination relations, or how can you combine the relations. Here we have seen so far that if Ramu drives a car, means here we are going to make an association between two entities. If multiple entities are there, how we can form a relation? Okay, that is what they call combining the relations. So if I say Ramu drives a car, that means Ramu may be a owner of that car. Ramu may be the driver of the car. Okay, Ramu may not own the car, but he may be driving the car. So you cannot clearly mention, okay, whether Ramu, in what way Ramu is belong to the car. Okay, what is the ownership of the car, whether the Ramu owns the car or not. So, but we can make a clarity on this particular thing with by combining the relations. There are two types, there are two ways to combine the relations, R1 and R2. These combining of the relations can be possible in two ways. One is via Boolean operations. We have seen the Boolean operations in the last lectures, that is union operations, intersection operations, minus, that is minus operation. These kind of operations we have seen. And another thing is to be composition operations. So composition is nothing but this composition relation you will get in many places in the computer programming and in object-oriented programming and analysis. In many places, especially in the software design, you will get this particular composition relation. So composition relation means is a part of relation. Composition relation is a part of a relation. That is what is called, wherever in any problem statement you will find part of relation. Okay, in such a cases you will use this composition relation. And there exists another relation called inheritance relation. Inheritance relation can also be defined with easy word in the problem statement. If I say Ramu is a good boy, so that means Ramu is inheriting the properties of the good boy. For example, in your mind, good boy means that fellow will be having some properties, like he has to neatly dressed up, he has to neatly do that, he has to attend the classes regularly. So this kind of some properties you have in mind. So when you say Ramu is a good boy, that means the properties of that what you are having was inherited by the Ramu. In the same way, composition will be represented in the problem statement with the help of has a relation. Okay, has a relation. Where in case of inheritance, is a relation. While coming to the composition, it is has a relation. Okay, we are not going to take any property. We are not that our entity is not inheriting or is not taking any property, but it is representing a part of relation. For example, car has 4 tires. Car has 4 tires. So whenever you find the word called has, immediately you have to think of that it is a composition relation. The car has 4 tires. Okay, there is a part of relation. Tires are the part of relation. Okay, here Ramu is a good boy means Ramu has a good boy is wrong. Ramu is a good boy means he is inheriting the properties of the good boy. Or it not. This is the very, very important thing in the computer programming and also in the object-oriented analysis and design, software design also. If you look at Java programming and any object-oriented programming, C++, where you use inheritance. Inheritance is a relationship. You are going to inherit the properties of the base class to the derived class. Okay. So if you want to represent the entire big class representation relation into a mathematical form, you can make it in a single line that this is the relation. C1 is the relation with C2 in a composite way. Means a big program with the different classes and methods can also be represented in a single line using mathematics. Okay, in this way. I hope by this time you got the understanding of where this exactly the relations has been used. Okay, especially in this composition relations. In general, the relations will be used in the databases also, in the social network analysis, in the networking analysis, and also identifying of the common points in the network. For example, you are the people who are sitting here and want to connect to the router of the university. Okay, there are several routers across the university. You want to connect to those routers. So here common points, you want to check for the common points. Here, multiple people, multiple users are connecting to the one particular common point. So this kind of things, any common point if you look at, so that can be represented using the relations. Okay. So this information is sufficient for you to go for the next slides. So there are two ways to combine the relations R1 and R2 via Boolean operators or via relation compositions. Now the combining relations via using Boolean operations, R1 is equal to 1, 1, 2, 2, 3, 3. While coming to the R2, 1, 1, 1, 2, 1, 3, and 1, 4. Then R1 union R2 is equal to combine both the sets. While coming to R1 intersection R2 means pick up the common pair available in the R1 and R2. And R1 minus R2 means you pick up the pair which is present in R1 and not in R2. Now combining the relations via relational composition, let R be a relation from set A to set B and S a relation from B to set C. The composite of R and S is the relation consisting of ordered pairs A comma C, where A belongs to, that is small a belongs to capital A, which is set A, small c belongs to capital C, where C is the element and capital C is the set, and for which there exists an element B belongs to capital B, such that A comma B belongs to capital R and B comma C belongs to S. We denote the composition of R and S as S, a small o symbol, and R. The composition between R and S will be represented in reverse way, that is S, small o, and capital R. You should not use capital O, capital R, small o, and capital S. If you represent like that, then it is the composition of S and R. Okay. If you want to represent composition of R and S, then you should represent in reverse. You should mention it in reverse. S, small o, capital R. That must be remembered. Computing the composite of two relations require that we find elements that are the second elements of ordered pairs in the first relation and the first element of ordered pairs in the second relation. This is very, very important to remember. The one who want to make note of this, they can note this. Computing the composite of two relations require that we find the first element that are the second element of the ordered pair in the first relation and the first element of the ordered pair in the second relation. For example, if I want to make the composition relation between the pairs A comma X and X comma B, then you look at A comma X, make note of this, A comma X and X comma B, then the composite relation will become A comma B. Okay. Computing the composite of two relations require we find the element that are the second element of the ordered pair in the first relation, that is X, and the first element of the ordered pair in the second relation. Now x comma b may, okay, x is the first element. So x was matched. So in such a cases, we'll make the composite ordered pair, that is a comma b. Okay. We'll see this in the next slides. Let R be the relation from a comma b, that is a to b, and S be the relation from b to c. Then A belongs to capital A, B belongs to capital B, and C belongs to capital C. Let A comma B belongs to capital R, and B comma C belongs to capital S. Then the composite of S, R, and S consists of the ordered pairs A comma C, because here A comma B belongs to R and B comma C belongs to S. Here the second element of the first order pair and the first element of the second order pair was matched. Then we'll make the composition relation, okay, of the R and S as A comma C. Okay. In this way, what you will identify? If I want to identify the relation between the parent and the child. Okay. So a lady and several childs. Okay. Lady, child, lady, child, lady, child. Okay. You may make the relation between. Okay. That lady may be mother of the child. Okay. That lady may be the grandmother of the child. So you may make several relations of that. Now I want to find who are the siblings. What are the elements who can identify as siblings? So obviously you are supposed to make the common parent. You have to identify the common parent. Then only you can make a relation that these two are the siblings, right? So in such a cases, okay, you will use this particular composition relations. Okay. Any instance of the application in computer science, when you find this kind of application, there you can use this composition relation. Okay. So we denote the relation S small circle R. That means the composition relation R and S. You have to read it in reverse. Note that S comes first when writing the composition. So this is another example in a mathematical representation. A comma B belongs to S circle R, that is S composition R, that is R, the composition relation between R and S. A comma X belongs to R and X comma B belongs to S. Just now as I given you an example, A comma X and X comma B. So then what could be the composition relation here? What will be the order pair you will get? A comma B. Now example here, R is equal to 1 comma 1, 1 comma 4, 2 comma 3, 3 comma 1, 3 comma 4. S is equal to 1 comma 0, S comma 0, 3 comma 1, 3 comma 2, 4 comma 1. Now what could be the composition relation between R and S? So find out the common ones. So here 1 comma 1 and 1 comma 0, 1 1 common, so 1 comma 0. Like that, you are supposed to add to the composite relation R and S, right? So like that, you find out what are the common things. That is the first, second element of the first order pair and first element of the second order pair. Whenever they match, then you make the pair in the composite relation. Now we have seen two different sets now. Now if what is the case if this is the same set? Okay, previously we have seen A cross A when belong to the same set. Okay, we have seen A cross B and many other things. Okay, and also we have seen the same sets. Now we are going to see the same set composing the parent relation with itself. Let R is the relation on a set A, that is capital R is a relation from a set A to itself. That means same relation to itself. The composition of R with itself always represented like this. Also, R composition R is sometimes denoted by R square. Similarly, R cube is equal to R square, composition relation with the R. and which can also be represented as composition relation of R and R and R, and so on. Thus, R power n is defined for all positive values of n. Let R be the relation on the set of all people such that A comma B belongs to capital R if a person A is a parent of person B. Just now, as I given you an example, sibling example. Sibling means two childs of belongs to common parent. So just like that. Then A comma C belongs to R composite relation R if and only if there is a person B such that A comma B belongs to capital R relation R and B comma C belongs to R. That is, if and only if there is a person B such that A is a parent of B and B is a parent of C. Now, in this way, you can find the grandparents also. Okay, so who is the grandfather, who is the grandmother, whether it is parental grandfather or maternal grandfather. So this kind of relations also you can identify. In other words, A comma C belongs to R composite relation R if and only if A is the grandparent of C. So combining the relations via relation composition, just we'll go through this. Let M be the relation. Whenever you mention the M as relation, it is said to be is mother of. F means is father of. Then what is M? Composite relation between father and mother. So M circle F means how you will read in reverse. Composite relation of F and M. Is mother of father. Is mother of is father. So if A comma B belongs to F, then A is father of B. If B comma C belongs to M, then B is mother of C. Then the composite relation F and M denotes relationship as maternal grandfather. Okay. And remember, this relations representation is very, very important, especially in case of artificial intelligence programming. Okay. When I'm discussing the course outline, on that day I told you how we will feed the robot with the relation rules. If so and so person comes and say hello, then what could be the name? And if so and so person comes and if it is identified as its owner, then how it has to react. Okay, and how the robot has to identify relation between two objects. So all these are the part of our computer science. So that is the reason, instead of representing the whole program when you write any documentation, you can make it as a set representation and you can represent in a sets in the set form or a relation form or maybe the any other discrete structure form that we study in this course. Okay. In the same way, what is F? What is the composite relation of mother and father? If A comma B belongs to M, then A is the mother of B. If B comma C belongs to capital F, then B is the father of C. Then the composite relation between M and F is relation of parental grandmother. Then what about M? The composite relation over M, that is mother over mother. So it will become maternal grandmother. So this is the way you will represent the relations. Given a relation R, the relation over relation will be represented as R square. Then R cube means the relation over R and R and R. So if you look at M cube means, what is the meaning? Mothers, mothers. So in short, R power n is represented as R power n plus R power n uh, with a relation, that is composite relation with r power n minus 1. Or you can say in a simple term, r power 1 is equal to r power n plus 1 is equal to r power n with relation with r. So here is some small example was given, 1 comma 1, 2 comma 1, 3 comma 2 and 4 comma 3. Then r square is equal to, you should find the common things, 1 comma 1 and 2 comma 1, 3 comma 1 and 4 comma 2. So like that the relations have been formed, and finally the R4 was calculated as R cube with relation R, then it is the same value you got here, R3, R cube. So finally, you consider this exercise for this lecture. Let R is equal to 1 comma 1, 2 comma 1, 3 comma 2 and 4 comma 3. What is R square and R cube? You can solve at your end. So this is related to the relations, inverse relations, and representing the combination of the relations. The relations are represented with the combination in a Boolean form or maybe in the composition form. We have seen the advantage of representing the relations in the composite form. Okay, that is, you want to make an analysis of the common relation between two or more different entities. Then we use this particular composition relation, and this also have the wide area of applications in the object orientation, artificial intelligence, network analysis, maybe social network analysis or general network analysis. So we'll see some more concepts related to the relations in the next lecture.